This is the video for section 7.1 in Math 1060. We'll be talking about angles, reviewing some things about angles, and then what we're going to do is see how we use angles in trigonometry, or how we view them. We're going to embed them inside the plane so that we can describe them in specific ways. So we're going to start out with the idea of an angle, which is going to have a common endpoint, and then you have two rays sticking out from the endpoint. Those rays can be defined by a point on each ray. So if we label these as, let's say, D, E, F, then what we can do is define the angle here using the notation angle D, E, F. And you may remember having seen this type of notation back when you took, say, a geometry class in the past. For trigonometry, it's going to make more sense for us to label angles with a single variable. And a lot of the time, we use Greek letters to denote angles. And so I'm just going to write down a few common ones that we use. We use the Greek letter theta a lot, Theta. And this angle is printed like this in your book. And when we write it, typically we get a little bit sloppy and we'll write it like that. There's the angle phi. Sometimes people call this phi. It looks like this. And when we write it, a lot of the time, again, we'll handwrite it something like that. Alpha, which is the Greek letter A, and that looks like this. Then we have beta, the Greek letter B, and it looks like this. And then we have gamma. And this is the Greek equivalent of the third letter of the alphabet, and we'll write it like that. Okay, so only two of them, theta and phi, look a little bit different written than they do printed. Okay, so the way that we describe angles in this class is going to be a little bit different than we would have described them in the past, like we did here in trigonometry. We're going to put angles in what we call a standard position. And in order to be in a standard position, an angle is going to be embedded in a two-dimensional plane, so the XY plane that we're used to from our previous algebra classes. And what we need is that the vertex, or the beginning point, is going to be at the origin. And then the second requirement is going to be that the initial side is on the positive x-axis. Okay, so if we look back up at this angle above, the initial side would be the starting side of this angle, and you'll notice we'll go from that side to the terminal side of the angle. And so in order to make this into a standard angle, what we would have to do is embed that in an XY plane so that that initial side is on the positive x-axis, right? This is our x-axis and y-axis. And that's the way we're going to draw angles in this class. And that's how we'll describe them. So for example, here, if I draw an XY plane, and let's say I have my initial side of that angle here on the positive x-axis, so that I can write this as a standard angle. And then I'll have the terminal side of that angle sticking off in some other direction. And then the angle itself is going to go from the initial side to the terminal side. So let's call this theta. Okay, so in order to be a positive angle, to be written as a positive angle, notice that this is going in the counterclockwise direction from the initial side. And we'll talk more about that later. So this beginning side is called the initial side. And then we have the terminal side. So that's terminology that we'll be using throughout the course. Okay, as I just barely mentioned, a positive angle is going to be one that is rotating starting from the initial side counterclockwise. So it extends counterclockwise. Okay, and then a negative angle would then extend clockwise, and we'll look at some examples of this. Okay, so we're given this first example that says to draw the angles in standard position. We're given 135 degrees and negative 60 degrees. Hopefully we remember degrees as a measure of angles from our previous courses. 135 degrees is 90 degrees plus 45 degrees. And so if we're going to draw this angle in standard position, we know its initial side is going to be there on the positive x-axis. And then if we have 135 degrees, that's going to be 90 degrees plus an additional 45. So we're going to end up somewhere right around there. And so our terminal side is going to be right about here. And since the angle is a positive number, 135, then we know that we're going to extend counterclockwise to draw this angle. So this is 135 degrees. Now on the second one, we're given negative 60 degrees. So we know this one is actually going to extend clockwise because it's a negative angle. And so we'll start at the positive x-axis again with our initial side, but this time we are actually going to extend clockwise 60 degrees. And 60 degrees is 2/3 of the way to 90 degrees. So it's going to be somewhere right about there. So let's draw that. And so our negative 60 degrees is going to be right about here. And we'll extend clockwise to denote that this is a negative angle. Okay, so we have 4 special angles that we call the quadrantal angles. And these are the angles that are going to lie directly on each of our axes. And so we'll draw these as follows. Let's see, I need to fit 4 of these here. So let's put 4 axis systems here. 1, 2, 3, and 4. The first quadrantal angle is going to be the one that just begins and terminates right at 0 degrees. This is a 0-degree angle. The second one terminates at straight up on the positive y-axis. That's going to be a 90-degree angle. The third one is going to terminate on the negative x-axis, and that's going to be a 180-degree angle. And then the fourth one is going to extend straight down, and so we can talk about that as a 180 plus an additional 90. So this would be a 270-degree angle. And those are our 4 quadrantal angles. Those are going to play important roles later on as we're learning about our trig functions. Our trig functions are going to operate on angles, and we'll want to remember how they operate on those quadrantal angles. Something that's really important for us to be able to do in trigonometry is to convert back and forth between degrees and radians. So radians are going to be a different way to measure angles. They're actually what you could probably consider as a more natural way to measure angles. When you think about it, we measure angles using this system where one complete revolution is 360 degrees. But that number 360 is somewhat arbitrary. Historically, I think it came from the Babylonians probably, who had a base 60 number system, and so 360 was a nice number in that system. But it's a little bit strange that we're still using it today, but it's what we're used to, right? And so in a lot of applications, people want to know angles in degrees, whereas more naturally in math, we describe them in terms of radians. And we'll find out later, in fact, even just later today, we'll see that a lot of formulas are more naturally written in terms of radians than degrees. And especially in calculus, For those of you that will be moving on to calculus, it makes way more sense typically to do calculus using this different way of measuring angles called radians. The idea behind radians is that we want to use arc length to measure angles. And this is going to be a little bit more natural than the idea of using degrees. So if we are to draw, let's say, a unit circle centered at the origin like this, then we can use arc length to describe angles here. So for example, let's say I have this angle with the beginning side on the positive x-axis, and say the terminal side is over here. Then we know how to describe that in terms of degrees, but you can also look at this as you have an arc length that starts here where the circle intersects the beginning side, goes around the circle counterclockwise, and ends where the circle intersects the terminal side. Now that segment, or that arc, I should say, on the circle has a length that you could measure. So if you had say a bendable tape measure, you could wrap it around there and see how long that is, and that's called the arc length. Now there's an issue though with trying to use the arc length to measure the angle, and that's that arc length is going to be different depending on the length of the radius, right? So the radius of that circle matters here. If I were to draw a smaller circle and look at that same angle, then what's going to happen is that arc is going to be shorter, and so then that's a challenge because we want to use the arc length to measure the angle, but just by changing the radius, we've changed the length of the arc length. And the way that we fix that so that we can use arc lengths to measure the angle is we measure them in the unit of the radius. So we define length 1 essentially to be the length of the radius. So instead of measuring in feet or inches or centimeters or meters, we're going to measure in terms of the length of the radius. So whatever the radius of that circle is, so if I draw another circle here, then that radius length is going to be the measurement for the length of the arc length. And so if we have an arc that is 1 radius length, then we're going to call that 1 radian. So we'll call that angle 1 radian. So this angle right here, where the length of that arc is the same as the radius, is going to be called 1 radian. And so now we can actually measure the angles on this circle in terms of radians. So for example, the angle right here that's double that beginning angle, that angle we're going to say is 2 radians, because it's the arc length here is 2 times the original length of the radius, right? And so that angle is 2 radians. Now, we're going to learn a little bit about how we can convert back and forth from these radian angle measures to degrees, and the other way around, from degrees to radians. And to do that, we need to remember what the formula is for the circumference of a circle. So recall, if you measure all the way around a circle, that length is actually measured in terms of the length of the radius, right? We say that it is that length c, the circumference, is 2 pi times the radius. And so one way to think about this is that the length all the way around a circle is 2 pi radians, right? And so how many radians equals 360 degrees? We can say that 360 degrees is 2 pi radians. And that leads us to a way to convert back and forth between radians and degrees. All right, so we're going to be using some special angles throughout this course. We use these particular angles because, first off, they're useful a lot in applications, but also they are they happen to be angles where the trig functions evaluate to really nice values that are easy to remember, or at least relatively easy to remember. So let's just draw 1/4 of this circle that's centered at the origin. And right here we have 0 degrees, and then we're going to split this up. We're going to have 45 degrees, which is right in between horizontal and straight up. We have 90 degrees here. And then right about here and here, we have two other special angles. We have 30 degrees and 60 degrees. We'll go ahead and write these here. So we have 0 degrees, we have 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Those are our special angles. Now, what we're going to do is rewrite these in terms of radians. 0 degrees is this angle right here, right? It starts and ends in the same place. There's no arc length, and so we're going to have 0 radians as well. Now, on the other hand, 30 degrees is going to be this arc length right here. Okay, and we can figure this out because we know that 2 pi is going to be equal 360 degrees. And so in order to get 30 degrees out of that, we need to divide both sides here by 12. And we'll get that pi over 6, which is 2 pi over 12, is going to be 30 degrees. And so we're going to say that 30 degrees is pi over 6 radians. Similarly, if you want to get 45 degrees, then you need to divide 360 degrees by, well, what would we divide that by? We're going to take it and we want to get 45. We would get 90 if we divided by 4, and so to get 45, we're going to divide by 8. And so we're going to take 2 pi over 8 is equal to 360 degrees over 8, and that says that pi over 4 is equal to 45 degrees. And so we'll have pi over 4 radians. Now 60 degrees is just double of 30 degrees, so that's going to be pi over 3 radians. And 90 degrees is what? That's 1/4 of 360. And so this is going to be 2 pi over 4, or pi over 2 radians. So it's going to be really important as we move forward to remember these values. So to convert back and forth between radians and degrees, like I've been doing here, you can use 2 pi equals 360 degrees, or it's a little bit more convenient to just say divide both of those by 2 and say pi is the same as 180 degrees. And so this is going to be our conversion. In fact, we could say pi radians is equal to 180 degrees, and then we'll use this as our unit conversion between radians and degrees. Okay, so let's make sure it's clear how we convert back and forth between radians and degrees using the following examples. The first one says just convert radians to degrees. And so we're given radians and we're supposed to round to the nearest degree as needed. So if we need any rounding, we'll be putting that in the calculator. Okay, so we're given pi over 5. And we're going to use something called dimensional analysis here. But the idea is going to be that we have our original angle is given to us in terms of radians, and we want to get rid of radians. And so we're going to multiply by a fraction that's going to be a change of unit fraction. And we want to put radians in the denominator of that fraction. And then we want to end up with degrees, right? And so we're going to put pi radians in the denominator. And we want to end up with degrees, and so we're going to put the equivalent in degrees on the top of that fraction, or the numerator. And so notice the units of radians, we can think of that as them canceling And then the remaining units are going to be the degrees, right? And then we're going to just multiply straight across the top of this fraction. So of these two fractions, so we have pi and we have 180 degrees. And then we have 5 times pi. And so we're going to actually cancel out the pi in the numerator, the pi in the denominator, and what we have left is just going to be 180 degrees over 5, right? And when we take 180 degrees and divide that by 5, we'll end up with exactly 36 degrees, and so there's no need to round here. So the answer here is going to be that pi over 5 converts to 36 degrees. They're the same thing, the same angle. Okay, the second one we're given is 8. Now you don't see any pi involved here, but the process is going to be exactly the same here. We're given 8 radians, right? And we're going to convert that to degrees. And so we need to put 180 degrees over pi radians. And the pi's don't cancel out this time. The units of radians still cancel. But there's only a pi in the denominator, so there's no cancellation of pi. And so we have 8 times 180 degrees in the numerator, and that is divided by pi. And so we can simplify that. It's said to round to the nearest degree as needed, and so what we can do is throw this in a calculator at this point. For this class, you'll want to use a scientific calculator that has a pi button, and when you do that, you're going to get approximately, it looks like 458 degrees. Okay, so now we're going to go back from degrees to radians. We can use the same conversion that we had before. Pi radians equals 180 degrees, except this time we're trying to get rid of the units of degrees and move to the units of radians. And since we want to cancel degrees, we're going to put 180 degrees in the denominator. That corresponds to pi radians in the numerator. And so we'll be able to cancel just like this, those units of degrees, and we'll have what, 20 pi over 180, and the units here will be radians. And when we simplify, I think 20 actually divides both the top and the bottom here, and then we'll have what, pi over 9 radians. Now something important here, a lot of the time when we write angles in radians, we actually drop this this radian, this symbol denoting that these are radians. A lot of the time we'll just write it as pi over 9, especially if we have pi in the final answer. That kind of gives us the hint that this is an angle written in terms of radians. Okay, so now we're going to look at negative 225 degrees, and our goal is to convert that to radians. So we're going to take pi radians, divide that by 180 degrees. That's going to cancel out our degree units, and we'll be moving to the units of radians again. And then we'll have what, negative 225 pi divided by 180, and this will be in radians, and this is, when we simplify, negative 5 pi over 4. Okay, so we have negative 5 pi over 4 radians here. The negative sign means the same thing that it did in degrees. It means we're going to start on the positive x-axis, but we're going to move in the clockwise direction to get to negative 5 pi over 4, which is somewhere right in there. Next, we'll be going through this idea of coterminal angles. So two angles are going to be considered coterminal angles if they land in the same place when you draw them in standard position. So for example, we could have the angle of 45 degrees, which puts us right about here, right? We start on the positive x-axis and then we go 45 degrees up to the terminal side there. But you can land on this same spot via a larger angle. So for example, if I go all the way around and then back to that point, this is a different angle. However, it lands in the same place. In fact, if I just add 360 degrees to 45 degrees, that's like going all the way around and then back to that spot again. So 405 degrees and 45 degrees are called coterminal angles because they land in the same place. They have the same terminal side. And we could draw another one. For example, if instead of going counterclockwise, we get to that terminal side by going clockwise and land in that same position, that's yet another angle, right, that is coterminal to the first two. And in fact, we would need to go negative 315 degrees to get to that angle. But you'll notice these three angles, they all differ by multiples of 316 or 360, right? By this distance all the way, or this angle all the way around to the same place, 360 degrees. Okay, so one of the things that's going to be important for us to do later on in this course is we're going to need to be able to take an angle and find the coterminal angle that's in a specific domain. So for example, if we want to find an angle between 0 and 365 degrees that's coterminal to the angle that we have. So here's an example of that. It says find an angle, alpha, coterminal with the angle 937 degrees, where 0 is less than or equal to alpha is less than 360 degrees. So we want an angle that's a positive angle that doesn't go, around more than once, and we're trying to figure out which angle in that domain gives you the same terminal side as 937 degrees. So one of the things that you could do is take 937 degrees and say, okay, that's larger than 360, so I could subtract 360 degrees from that, right? Excuse me. Now, when you do that, you're still going to get a number that is larger than 360 degrees. But if you take this, so that's still larger than 360 degrees. But if you take 937 degrees and subtract 360 degrees twice, so you sort of unwind back around twice, then you're going to get 937 minus 720, which ends up giving you 217 degrees. That's an angle between 0 and 360, and so that's the angle that we're looking for. That's the coterminal angle that satisfies that it's between 0 and 360 degrees. Okay, let's look at another example. This time we're given a negative angle, negative 3 pi over 2, and we're supposed to figure out a coterminal angle, beta, that is between 0 and 2 pi. So notice when we say between 0 and 2 pi, that's the same as saying between 0 and 360 degrees before, just written in terms of radians, right? It's between 0 and 2 pi now. Okay, so we had negative 3 pi over 2. That's less than 0, and so we need to be adding, we need to be unwinding back around in terms of multiples of 360 degrees. But now we're writing in terms of radians, and so we're going to say we're going to add multiples of 2 pi. So if I take negative 3 pi over 2, I can find a coterminal angle by adding 2 pi to that, which is the same as adding 4 pi over 4. We can get a common denominator. So we have negative 3 pi over 2 plus 4 pi over 4. I'm going to add those and I'm going to get what? Positive pi over 2. That's an angle in between 0 and 2 pi, and so that's the coterminal angle that we're looking for. Now, as a final topic in this section, what we're going to do is look at two formulas involving circles, and these two formulas actually need to be written in terms of radians, or at least it's easier to write a natural-looking formula in terms of radians. And so here's the idea. our first picture is going to be just a circle. And what we care about here is an arc length on that circle, measuring the arc length. And so the idea is that we have, some arc length on there, and we have some angle, which we'll call theta, and we have the radius. We know the radius, and we know the angle, and we want to find the arc length, which is often written as S, right? And so we want to write S in terms of what we know, which is the radius and the angle. Now we know the answer to this in one specific case, right? If you want to find the arc length all the way around the circle, that would be the same thing as the circumference of the circle, right? But we know the circumference is 2 pi times the radius, right? 2 pi r. But notice 2 pi is actually just the angle all the way around the circle, right? Written in terms of radians. And it's going to be the same thing here. Instead of writing 2 pi though, we're just going to replace it with our angle. So we have theta times the radius, right? And so if theta happens to be 360 degrees or 2 pi, then we're going to end up with the circumference of the circle. But if it's smaller, then we're going to end up with this arc length here. Okay, now the other formula that's also to do with the circle is going to be looking at this same picture. Instead of finding the arc length, we're going to find the area of that sector or pie slice, right? Thinking about this as a slice of pie, this area is what we want to find. Now, we're going to assume again that we have the angle, theta, and we have the radius. Now, assuming that we have both of those, we can take the area and write it as follows. Well, before we do, let's think about if our angle theta happens to be, all the way around the circle, 360 degrees or 2 pi, then we know that the area of a circle is what? 1/2, is pi r squared, right? Just pi r squared. So if our angle is 2 pi, then we're going to have pi times the radius squared. Now, pi is 1/2 of that angle 2 pi. And so in general, what we're going to do is we're going to take 1/2 of our angle, theta, right, and multiply that by the radius squared. And now we'll get a formula for the area of the sector or the pie slice of that circle. Now, it's really important here to realize, though, these two formulas are written naturally in terms of radians. So this angle theta needs to be in radians in both cases, in both of these formulas. So if you're given if you're given the angle in terms of degrees and you're asked to find the arc length or the area, then what you want to do is first convert that angle into radians, and then you can use these formulas. So here's an example where we have to do that. So this says find the arc length S and the area A of the sector of a circle of radius 4 centimeters subtended by a 150 degree angle. So here we have our circle. We're given a 150 degree angle, which looks something like that. I don't know. But here, this is 150 degrees. But the issue is that we don't want our angle to be written in terms of degrees. We want theta to be written in terms of radians. So what we're going to do is take 150 degrees, and then we've practiced already switching that to radians. What we need to do is put pi radians in the numerator because we want to switch to radians, and then we'll put the equivalent degrees, so 180 degrees, in the denominator. And so we'll get 150 pi over 180 for our angle theta. And those are both divisible by 10, so we could put this as 15 pi over 18. Actually, they're both divisible by 3 as well, so we'll get, 5 pi sixth, and then that's reduced. And now what we can do is we can put that into our two formulas. The first formula for the arc length was what S is equal to the radius times theta, where theta needs to be written in terms of radians like we've done. Or sorry, yeah, so the radius was what, 4 centimeters. I'm going to keep the units in there so that we have our correct units in our final answer. And then we have theta, which is 5 pi over 6. Okay, so when we multiply those two together, we're going to get, what, 20 pi over 6 or 10 pi over 3 centimeters. It doesn't actually tell us to round here, so we could leave it as this exact answer. If we wanted to know, to know what we have in centimeters for an application, we would need to round this then to whatever number of decimal places we need, right? But this is the exact answer. Okay, so a lot of the time this semester I'm going to ask you for the exact answer. And what I mean by that is that you don't do any rounding in the answer. So here, 10 pi over 3, that is the exact answer, and we can get as many decimal digits of accuracy as we need for our application from that answer. But if we were to take this and round it, then we've lost that accuracy and we can't, let's say we round it to 1 decimal place. Well, if we end up needing 2 decimal places our for our application, then that second decimal place is lost, right? And so that's why we call this an exact answer. You can always recover as many decimal places of accuracy as you need from it. Okay, so we have S. Let's compute the area of that sector, or the pie slice. Okay, so the area was what? The formula was 1/2 times theta times the radius squared. Theta here being what? Theta needs to be the angle written in radians, which we have as 5 pi over 6. So we have 1/2 times 5 pi over 6, and now we have what, 4 centimeters. And I'm going to take that entire quantity and square it. And I'm going to also square the units because that's going to tell me the units of our final answer. And so we're going to have, well, let's do some simplification here. You have, across the top, you're going to have 20 pi, and across the bottom, you have 12. Oh, no, I need to square. Let's square what we have in the parentheses at the end first. So we have 1/2 times 5 pi over 6 times 16 centimeters squared, right? I need to take that exponent, I'm squaring the 4, and I'm putting a square on the centimeters because our units now are going to be centimeters squared. Now I can start combining, right, and simplifying. So what do I have here? This is 16 times 5 over 12. So we'll have 16 times 5 pi over 12, and we need to start simplifying that. And so what can we do here? We can divide these two both by 4. That's going to give us 4 over 3. So it looks like we're going to have 4 times 5, which is 20 pi over 3 centimeters squared. Again, this is the exact answer, and if you have an application, you'll probably round that to however many decimal places you need for that application.